like 1.2.3 practice problems. So right now we'll go through the equations first. These are the gas laws from chemistry. Hopefully you've seen them before. First one is pressure 1 over temperature 1 equals pressure 2 over temperature 2. Next one we've got volume 1 over temperature 1 equals volume 2 over temperature 2. And last one, pressure 1, volume 1 equals pressure 2, volume 2. And so for that one, the pressure and temperature, the volume is going to be held constant. For this one, the pressure would be held constant. And for this one, the temperature would be held constant. And the units don't matter as long as they're the same. You have the same units for pressure on both sides, same units for temperature on both sides, same units for volume on both sides. The temperature, however, needs to be an absolute temperature scale. Oops. So Kelvin or degrees Rankine, not Fahrenheit or Celsius. Make sense? Alright, and our last equation is one you probably haven't seen before. Q equals area times velocity. And Q is going to be the flow rate. That's going to be in some volume over time. So an example would be like gallons per minute or inches cubed per minute or something like that. A is area. Actually, I should call that A is cross-sectional area. So I should refer to it. And then V is velocity of the fluid. That's going to be in something like meters per second or inches per minute or something like that. Any question over these equations? Yeah, I may have you know those at some point, not for like the group quiz tomorrow or anything like that. So first problem, the pressure of a gas is 17 psi and the temperature is 160 degrees Fahrenheit. The pressure is increased to 20.84 psi. What is the new temperature in Fahrenheit? And we're assuming in this one the volume is held constant. Oops. Alright, is 160 degrees Fahrenheit the units you want for that? No. We'd like to get to Rankine for this class. Kelvin would work too, but it's a little harder to go from like Fahrenheit to Celsius, Celsius to Kelvin, then we're going to have to go back again. So we'll say temperature 1 is 160 degrees Fahrenheit. What do we add to that to get to Rankine? Anybody remember? 460. So that equals 620 degrees Rankine. So then we're going to do pressure 1, so 17, over temperature 1, which is 620. That's psi. Degrees are 20.84 psi for temperature 2. And what do we get for temperature 2? So 160 degrees Rankine. So subtract 460 from that to get to Fahrenheit. So temperature 2 is 300 degrees Fahrenheit. But I just said in Fahrenheit. So normally I'd accept any temperature unless specified. Any questions? Alright, So a gas is initially at 200 degrees Fahrenheit in an 85, that should be inches cubed container. It doesn't translate well when I put it into this program. The volume is held in the container is decreased to 14 inches cubed while the pressure is held constant. What is the new temperature in Fahrenheit? So we gotta convert temperature again. So temperature is going to be 200 degrees Fahrenheit plus 460 equals 660 degrees Rankine. So I do volume over temperature equals volume over temperature. So our volume 1, let's do volume 1 is 85 inches cubed over 660 Rankine equals 14 inches cubed over temperature 2. And what do we get for temperature 2? (108.7 degrees Rankine), and we subtract 460 from that. How do we get, Sean? Negative 351 degrees Fahrenheit. That is very cold. Yes. But possible. Alright, this time we have a gas at a pressure of 32 psi at a volume of 33 inches cubed. What will the new pressure be if the container size is decreased to 13 inches? So again, temperature should be constant on this one. So T is equal to constant. Alright, so we've got our pressure 1. So we use pressure 1 times volume 1 equals pressure 2 times volume 2. So pressure 1 is 32 psi times volume 1 is 33 inches cubed equals pressure 2 times 13 inches cubed for volume 2. And what do we get for pressure 2? 81.2 psi. Any questions on that one? So last one here, the flow rate in a pipe is 16 gallons per minute, and the radius of the pipe is 3.7 inches. What is the velocity of the fluid in the pipe in inches per minute? Alright, this one's a little trickier. So first thing we gotta notice is this is in gallons per minute. It gives us the radius in inches and the velocity of the fluid in inches per minute. We'd much rather have things in like inches cubed for our volume than in gallons. So that's why they give us 1 gallon equals 231 inches cubed. So if we say our flow rate Q is 16 gallons per minute, we'd like to get to inches per minute, or inches cubed per minute, because that's what we're trying to get to inches per minute. So if we say times 231 inches cubed in 1 gallon, the gallons cancel, and we're left with what's 16 times 231? 3696. That says inches cubed of fluid per minute. Any questions on what we did there? Alright, we also need the cross-sectional area of the pipe. How can we find the cross-sectional area of the pipe? So pi r squared equals pi times our radius, 3.7 inches squared. No, we want it as a decimal. 43 inches squared for the cross-sectional area. Then we do Q equals area times velocity. And our Q is 3696 inches cubed per minute. Equals area is 43 inches squared. And our velocity is what we're looking for. So what's our velocity? Yep, 85.95 inches per minute. That means therefore. So instead of writing it underneath, because I would have ran out of room, I just shifted it over there. So you can think about the dots as just like it should be another line, but space requires me to put it over there. Alright, any questions on this one?